Hi everyone, and welcome to Sleep and Learn. Here's a beautiful thought to begin with. Some comets have been traveling through darkness for billions of years, carrying ice and dust older than Earth itself. Then, as they approach the Sun, they suddenly awaken, forming glowing clouds and tails that can stretch for millions of kilometers. So get comfortable, relax, and let's follow these ancient travelers through the quiet depths of space. Visitors from another star. Just imagine this for a moment. Somewhere far beyond our Sun, near a star we may never see with the naked eye, a small frozen world was quietly drifting through the darkness. Then, after an ancient gravitational disturbance, it was thrown into interstellar space. For millions, or perhaps billions, of years, it traveled alone between the stars, until one day it entered our solar system. There is something deeply peaceful about comets. They move through the darkness without hurry, carrying ice, dust, rock, and memories from places unimaginably far away. Some belong to our own solar family, but a few may be true visitors from other star systems. For most of human history, every known comet was assumed to orbit the Sun. Some returned regularly, while others followed enormous paths that took thousands of years to complete. But in 2017, astronomers discovered something completely new. A strange object was moving rapidly through the solar system. It followed a path that could not be explained by a normal orbit around the Sun. Instead of circling back, it was passing through only once. It had arrived from interstellar space and would soon disappear into the darkness again. Astronomers named it Oumuamua, a Hawaiian word often translated as a messenger or scout arriving from the distant past. Oumuamua did not look exactly like a familiar comet. It showed no obvious bright coma, the glowing cloud of gas and dust that normally surrounds a comet near the Sun. It also had no clearly visible tail. Its brightness changed dramatically as it rotated, suggesting that it may have had an unusually elongated or flattened shape. Scientists debated whether it was a rocky asteroid, an inactive comet, or something even more unusual. Its motion showed a small acceleration that gravity alone could not fully explain. On ordinary comets, such acceleration can happen when sunlight warms the surface and causes gases to escape. These gentle jets act like tiny natural thrusters. Yet no strong cloud of gas was detected around Oumuamua. This mystery inspired many explanations. Perhaps it contained forms of ice that were difficult to observe. Perhaps it released hydrogen or another invisible gas. Perhaps it had a light, porous structure shaped by long exposure to cosmic radiation. Even today, its exact nature remains uncertain. But one thing is clear. It came from beyond our solar system. Only 2 years later, astronomers discovered a second confirmed interstellar visitor. This one looked much more like a traditional comet. It was named 2I Borisov, after the amateur astronomer Gennady Borisov, who first noticed it in 2019. The letter I stands for interstellar, and the number 2 shows that it was the second confirmed object of this kind. Unlike Oumuamua, Borisov developed a visible coma and tail as it approached the Sun's sunlight warmed its frozen surface, releasing gas and dust into space. For a brief time, astronomers could study material formed around another star. That is one of the most extraordinary facts about interstellar comets. When we observe them, we are not simply looking at distant objects. We are examining physical pieces of other planetary systems. The atoms inside Comet Borisov may have once floated inside a cold cloud surrounding a young alien star. They may have existed near planets we will never visit. Then gravitational interactions, perhaps involving a giant planet, threw the comet away from its original home. This kind of ejection is probably common. During the formation of planetary systems, young planets move through disks of dust, gas, and icy debris. Large planets can disturb smaller objects, changing their orbits. Some are sent inward toward the star. Others are pushed outward. A few may gain enough speed to escape the system entirely. Our own solar system has likely released countless comets into interstellar space. Right now, tiny frozen fragments from the distant past of the Sun may be wandering near other stars. Perhaps, somewhere, astronomers on another world are observing one of our ancient comets. Interstellar space may therefore contain an enormous population of dark, frozen travelers. Most are too small and distant to detect. They pass silently through the galaxy, illuminated only when they move close to a star. A comet may spend almost its entire existence in darkness. Far from any sun, its gases remain frozen. It produces no tail and no glowing coma. It may look like nothing more than a faint lump of ice and rock. But when it enters the warmth of a star, it begins to transform. Ice turns directly into gas. Dust rises from the surface. A hazy atmosphere forms around the nucleus. Then radiation and the solar wind push material outward, creating a tail that may stretch for millions of kilometers. The comet becomes visible not because it burns, but because sunlight awakens it. This transformation is temporary. As the comet travels away again, it cools. The jets weaken. The coma fades. The tail disappears, and the comet returns to darkness. Interstellar visitors remind us that star systems are not completely isolated islands. Material can move between them. Pieces of one solar system can cross the silent ocean of the galaxy and enter another. Some scientists have even wondered whether comets could transport complex organic molecules between star systems. Comets are known to contain carbon-rich compounds, water ice, and other ingredients associated with chemistry important to life. This does not mean that life itself commonly travels on comets. Interstellar space is harsh, filled with radiation and extreme cold. But the possibility that chemical ingredients can move between stars is scientifically fascinating. Each comet is like a sealed capsule from another time. The comets of our solar system preserve material from its earliest formation, more than 4.5 billion years ago. An interstellar comet may preserve material from the birth of a completely different star. And so, when one of these rare visitors appears, astronomers watch carefully. They measure its speed, study its gases, examine its dust, and try to understand the distant place where it began. Then the visitor moves on. It does not remain for long. It passes the Sun, crosses the planetary region, and continues outward on a path that may never bring it close to another star again. There is something calming in that endless journey, a small frozen world moving quietly between suns, carrying the story of one star system into the darkness of another. How a comet begins to glow. A comet can spend almost its entire life hidden in darkness, so cold and distant that nothing around it seems to move. But as it approaches the Sun, something beautiful begins to happen. Slowly, quietly, the frozen surface wakes up. Far from the Sun, a comet is mostly a dark nucleus made of ice, dust, rock, and frozen gases. It may be only a few kilometers wide, and its surface is often blacker than coal because it is covered with ancient carbon-rich material. In that distant cold, it reflects very little light and can be extremely difficult to detect. Then the comet begins to move inward. Sunlight grows stronger. The temperature rises. Frozen substances such as water, carbon dioxide, carbon monoxide, and other volatile materials begin to change directly from solid ice into gas. This process is called sublimation. Unlike melting, sublimation skips the liquid stage. The ice does not become a puddle. It turns straight into vapor. As gas escapes from beneath the surface, it carries tiny grains of dust with it. These particles spread outward and create a vast, faint cloud around the nucleus. This cloud is called the coma. The coma can grow far larger than the solid body at its center. A nucleus only a few kilometers across may become surrounded by a glowing atmosphere tens of thousands, or even hundreds of thousands, of kilometers wide. In some cases, the coma can become larger than Earth. This is one of the most surprising things about comets. The bright object seen in the sky is not simply the icy nucleus. The nucleus itself is usually too small and too dark to see clearly from Earth. What we notice is the sunlight reflecting from the dust and interacting with the gas around it. The comet appears to glow, but it is not burning like a piece of wood. Its light comes mostly from reflected sunlight and from energized gas molecules. Ultraviolet radiation from the sun can break apart molecules in the coma and excite atoms and ions. When those particles release energy, they can emit faint colors. Different gases may produce different shades. Some comets show greenish comas because of molecules containing carbon, especially diatomic carbon. Others may appear bluish because of ionized carbon monoxide. The colors are often subtle to the human eye, but cameras and telescopes can reveal them more clearly. As the coma grows, the comet begins to develop its most famous feature, the tail. In reality, many comets have two main tails. The first is the dust tail. It is made of tiny solid particles released from the nucleus. Sunlight pushes gently on these grains through radiation pressure. Because dust particles still follow their own curved paths around the sun, the dust tail often appears broad, soft, and slightly curved. The second is the ion tail, sometimes called the plasma tail. It is made of electrically charged gas particles. These ions are swept away by the solar wind, a continuous flow of charged particles streaming outward from the sun. The ion tail is usually straighter and narrower than the dust tail. It may also appear blue in photographs. Both tails always point generally away from the sun. This means that a comet's tail does not simply trail behind it like smoke behind a moving train. When the comet approaches the sun, the tail may stretch behind it. But after the comet passes the sun and begins moving outward, the tail can appear to lead the comet. The sun determines the direction. This is why comet tails can seem so strange. Their shape depends not only on the comet's motion, but also on sunlight, the solar wind, and the size and type of particles being released. Some comets develop more than two visible structures. They may show multiple dust streams, curved bands, narrow jets, or even temporary spikes. These features can change from night to night because the nucleus rotates. As different regions turn toward the sun, fresh jets of gas and dust can erupt from cracks, cliffs, and pits. A comet nucleus is not always smooth. Space missions have shown that comet surfaces can be rugged, fractured, and dramatic. There may be steep cliffs, flat dusty plains, shadowed cavities, and strange boulder fields. When sunlight reaches an active patch, gas pressure can lift material into space. The rotating nucleus then sweeps these jets around like a slow sprinkler. This can create fans, arcs, and spiral patterns inside the coma. Astronomers study these shapes to estimate how fast the nucleus is rotating and where its most active regions are located. The coma itself is constantly changing. Close to the nucleus, particles collide more often and move through relatively dense gas. Farther away, the cloud becomes thinner and more diffuse. Eventually, sunlight and the solar wind carry the material into the tail. A large comet can release enormous amounts of water vapor and dust near the sun. Yet compared with the total size of space, even a brilliant comet is still incredibly delicate. Its tail may stretch for millions of kilometers, but the material inside it is extremely thin. If a spacecraft passed through a comet tail, it would not encounter anything like a thick cloud on Earth. The particles are spread far apart. The tail looks bright because it covers such an enormous distance and because sunlight illuminates countless tiny grains. A comet may lose part of itself each time it approaches the sun. The heating causes ice to escape, dust to break away, and the surface to erode. Over many passages, a comet can become less active. Its volatile materials may be exhausted, leaving behind a dark object that resembles an asteroid. Some comets also break apart. The stress of heating, spinning, and gas pressure can fracture the nucleus. Large pieces may separate, each producing its own coma and tail. At other times, a comet may pass so close to the Sun that intense heat and tidal forces destroy it completely. But before that happens, it may become spectacularly bright. The brightness of a comet is difficult to predict. A newly discovered comet may be expected to become brilliant, then remain faint. Another may suddenly brighten after an outburst. Outbursts happen when fresh ice is exposed or when trapped gas escapes from beneath the surface. In a short time, the comet can release a new cloud of dust and become many times brighter. This unpredictability is part of their charm. Comets do not follow a perfect performance. They respond to sunlight in their own way. Some remain modest and quiet. Others grow long tails that cross a large part of the sky. And yet, every glowing comet is created by the same gentle process. A frozen body approaches the Sun, ancient ice turns to gas. Dust rises. A cloud forms. Light catches the particles, and the darkness begins to shine. For a brief time, something that spent millions of years nearly invisible becomes one of the most beautiful objects in the night sky. The comets humanity never forgot. Some comets appear so rarely that a person may see them only once in a lifetime. Others return again and again, following long paths around the Sun like quiet celestial visitors keeping an ancient appointment. Among all known comets, none is more famous than Halley's Comet. For thousands of years, people saw it without understanding that each appearance belonged to the same object. Ancient observers in China, Babylon, Europe, and other parts of the world recorded a bright comet crossing the sky. Sometimes it was treated as a warning, sometimes as a sign of change. But no one yet knew that it would return. That changed because of the English astronomer Edmund Halley. Using the laws of motion and gravity developed by Isaac Newton, Halley studied reports of comets seen in 1531, 1607, and 1682. He noticed that their paths were remarkably similar. From this, he proposed that they were not three different comets, but the same comet returning periodically. Halley predicted that it would appear again around 1758. He did not live long enough to see his prediction confirmed, but the comet returned almost exactly as expected. This was a major moment in astronomy. It showed that comets were not mysterious objects appearing without order. They obeyed the same gravitational laws as planets. Today, the comet bears Halley's name. Halley's Comet completes one orbit around the Sun roughly every 75 to 76 years, although the exact timing changes slightly because of gravitational interactions with planets. Its orbit carries it far beyond Neptune before bringing it back toward the inner solar system. Its nucleus is about 15 kilometers long and shaped somewhat like an irregular peanut or potato. When the Giotto spacecraft flew past Halley in 1986, it revealed a dark, rugged body releasing bright jets of gas and dust. The nucleus reflected only a small fraction of the sunlight that reached it. It was darker than many people had imagined. The brilliant appearance of Halley's Comet comes not from the solid nucleus itself, but from the enormous coma and tail that form when it approaches the Sun. Its next return is expected in 2061. For some people alive today, that appearance may become a deeply personal connection between generations. Someone who saw Halley's Comet as a child in 1986 may watch it again as an older adult. A comet can therefore become a kind of cosmic clock, marking the passage of a human life. Another unforgettable comet was Hale Bopp. It was discovered independently in 1995 by Alan Hale and Thomas Bopp. At the time, it was still very far from the Sun, yet it was already unusually bright. Astronomers soon realized that it could become a spectacular object. And it did. During 1996 and 1997, Hale Bopp became one of the most widely observed comets of the 20th century. It remained visible to the unaided eye for many months, giving people around the world plenty of time to look up and find it. Hale Bopp had a bright coma and two prominent tails. Its dust tail appeared pale and curved, while its ion tail looked straighter and often showed a bluish color in photographs. The comet's nucleus was unusually large, perhaps around 60 kilometers across, although estimates vary. Its size and activity helped it remain bright even while it was still far from the Sun. Hale Bopp will not return soon. Its orbit was altered by interactions with the planets, and it may take more than 2,000 years to complete another journey around the Sun. The people who next see it will live in a world very different from ours. That thought gives the comet a strange kind of calmness. It is moving now through the distant solar system, gradually fading, carrying away the sunlight it briefly reflected toward Earth. More recently, Comet NEOWISE offered another memorable display. Officially known as C-2020 F3, it was discovered in March 2020 by NASA's Near-Earth Object Wide Field Infrared Survey Explorer spacecraft. At first, astronomers were unsure whether the comet would survive its close passage around the Sun. Many comets become weak, fragment, or fade before reaching their brightest point. NEOWISE survived. During July 2020, it became visible from many parts of the Northern Hemisphere. People saw it near the horizon in the early morning and later in the evening, often beneath the familiar stars of the Big Dipper. Its golden dust tail stretched gracefully across the sky, while photographs also revealed a fainter blue ion tail. For many observers, NEOWISE was their first naked-eye comet. Unlike stars and planets, which may look almost unchanged from night to night, the comet seemed alive. Its position shifted. Its tail changed shape. Its brightness slowly faded as it moved away from the Sun. NEOWISE will not return for thousands of years. Its long orbit may carry it back toward the inner solar system in roughly 6 or 7 millennia. No one living today will see that return, and the names of our cities and countries may be forgotten by then. Yet the comet will continue along its path. Famous comets often become part of human history because they are both predictable and fleeting. They may arrive after centuries of darkness, appear for a few weeks or months, and then disappear again. Some become famous because they are bright. Others because they are scientifically unusual. Comet Hyakutake, for example, passed relatively close to Earth in 1996 and produced an extraordinarily long tail. Comet McNaught became a magnificent sight in the Southern Hemisphere in 2007, displaying a broad, curved fan of dust. Comet Shoemaker Levi 9 became famous for a very different reason. It broke into fragments and collided with Jupiter in 1994. Astronomers watched dark impact marks appear in Jupiter's atmosphere, some larger than Earth. This event reminded scientists that comets are not only beautiful visitors. They are also active participants in the solar system, capable of delivering enormous energy when they collide with planets. But most comets pass without danger. They remain far away, tracing silent arcs through space. Their names are often taken from the people or instruments that discovered them, preserving a small human story inside a much larger cosmic journey. Each famous comet connects different times. Ancient observers watched Halley without knowing where it came from. Modern spacecraft photographed its nucleus. Future generations will see it return. Hale Bopp shone over the end of the 20th century and is now traveling into the cold outer darkness. NEOWISE appeared briefly in the modern world, photographed above mountains, lakes, houses, and quiet roads. Comets pass above every kind of human life. They do not belong to one country, one culture, or one century. They are shared visitors, seen by anyone willing to step outside, wait for their eyes to adjust, and look patiently into the night. And perhaps that is why the most famous comets remain in memory. They remind us that some of the most beautiful things in the universe do not stay. They arrive softly, glow for a little while, and continue on their way. When comet dust becomes a meteor shower. Sometimes, a comet leaves behind something more lasting than a glowing tail. As it travels around the Sun, it releases tiny grains of dust, fragments of rock, and particles of ancient material. These pieces spread slowly along the comet's orbit, forming a long, invisible stream through space. Most of the time, we cannot see this trail at all. But when Earth passes through it, the night sky begins to sparkle. This is how many meteor showers are born. A meteor shower does not happen because dozens of stars are suddenly falling. The bright streaks are caused by small particles entering Earth's atmosphere at tremendous speed. Most are no larger than grains of sand. Some are as tiny as dust. Yet even such small particles can create brilliant flashes. When a meteoroid strikes the atmosphere, it moves so quickly that the air in front of it becomes compressed and intensely heated. The particle and the surrounding gases begin to glow, producing the streak of light we call a meteor. The meteor is not usually the object itself burning like a piece of wood. Much of the light comes from heated and ionized air. Most particles disappear high above the ground. They enter the atmosphere at altitudes of around 100 kilometers and usually vaporize long before they can reach Earth's surface. A person watching from below sees only a quiet line of light, sometimes lasting less than a second. And yet that tiny flash may have begun its journey inside a comet billions of years ago. Meteor showers occur at roughly the same time each year because Earth follows the same orbit around the Sun. When our planet reaches a stream of comet debris, many particles enter the atmosphere from similar directions. To an observer, the meteors appear to spread outward from one point in the sky. This point is called the radiant. Meteor showers are usually named after the constellation near their radiant. The Perseids appear to come from the constellation Perseus. The Leonids seem to radiate from Leo. The Orionids appear near Orion. But the particles themselves are much closer than the stars of those constellations. The constellations simply provide a convenient background and direction. One of the best-known annual showers is the Perseid meteor shower. It is created by debris from Comet Swift-Tuttle, a large comet that completes an orbit around the Sun roughly every 133 years. Each time it passes through the inner solar system, it releases more dust into its orbital trail. Every August, Earth crosses part of this stream. Under dark skies, the Perseids can produce dozens of visible meteors per hour. Many are fast and bright. Some leave glowing trails that remain visible for a few seconds after the meteor itself has vanished. These lingering trails are called persistent trains. They form when the meteor changes the chemistry and electrical state of the upper atmosphere. Winds can twist and reshape them, creating delicate glowing curves in the sky. Another famous meteor shower is the Leonids. The Leonids come from Comet Tempel-Tuttle. In most years, the shower is modest. But occasionally, Earth passes through an especially dense region of debris, and the Leonids become a meteor storm. During a meteor storm, hundreds or even thousands of meteors may appear in a single hour. Historical accounts describe extraordinary Leonid storms. In 1833, observers across North America reported a sky filled with so many meteors that some people thought the stars themselves were falling. The event helped transform the scientific understanding of meteors. Astronomers began to recognize that these displays were connected to space and occurred in predictable patterns. The Orionid and Eta Aquarid meteor showers both come from Halley's comet. This means that even when Halley itself is far away and invisible, Earth still encounters material it left behind. The Orionids appear in October, while the Eta Aquarids are most active around May. They occur at different times because Earth crosses two separate parts of Halley's long orbital path. A person does not need to wait until 2061 to experience a piece of Halley's comet. Its dust arrives every year. The Geminids are unusual because their parent body is not an active comet in the traditional sense. They are linked to an object called 3200 Phaeton, which behaves somewhat like an asteroid but may release material when heated by the sun. This makes Philae a mysterious object somewhere between a comet and an asteroid. The Geminids occur in December and are often among the strongest meteor showers of the year. Their meteors can appear slower and brighter than those of many other showers because of the speed and angle at which the particles meet Earth. Meteor showers vary from year to year. Their visibility depends on how dense the debris stream is, how dark the sky is, whether radiant appears above the horizon, and whether the moon is bright. City lights can hide many faint meteors. In a truly dark place, the sky may reveal far more. The best way to watch a meteor shower is often the simplest. No telescope is required. Telescopes show only a small area of sky, while meteors can appear almost anywhere. A wide, open view is better. The observer can lie back, allow the eyes to adjust to darkness, and wait quietly. At first, perhaps nothing happens. Then a thin streak crosses the sky. A few minutes later, another appears in a different direction. Some are faint and quick. Others are bright enough to cast a momentary shadow. Each meteor lasts only briefly, which is part of its beauty. There is no time to study it closely or hold on to it. It appears, shines, and is gone. Scientists, however, can learn a great deal from meteor showers. By studying their speed and direction, astronomers can reconstruct the orbits of the particles. By analyzing the light, they can estimate what elements are present. Different colors can be produced by sodium, magnesium, iron, calcium, and gases in Earth's atmosphere. Meteor observations can also reveal changes in comet debris streams. A comet's trail is not perfectly smooth. Giant planets, especially Jupiter, can pull on the particles and shift their paths. Over time, the trail becomes stretched, twisted, and divided into denser and thinner regions. This is why some years bring stronger displays than others. A meteor shower is therefore a meeting between two moving histories. Earth continues around the Sun, following its familiar yearly path. The comet's dust follows another path, shaped by ancient activity and gravity. At one particular place in space, these two journeys cross. The result is light. It is strange to think that something so small can be seen from so far away. A particle smaller than a pebble can create a streak visible across hundreds of kilometers of Earth's surface. The darkness makes it noticeable. For a fraction of a second, a grain of comet dust becomes brighter than many stars. Then it disappears into the atmosphere, leaving no sound and almost no trace. Meteor showers are reminders that comets do not pass through the solar system without leaving memories behind. Their dust remains on invisible roads around the Sun. Earth crosses those roads again and again, gathering tiny fragments of ancient worlds. And on quiet nights, those fragments return as light. Rosetta and the little lander that touched a comet. Imagine trying to catch a dark, frozen world moving through space at tens of thousands of kilometers per hour. Now imagine not only catching it, but traveling beside it for months, studying its surface, and gently placing a small laboratory upon it. That is exactly what the Rosetta mission attempted. Rosetta was one of the most ambitious comet missions ever created. Built by the European Space Agency, it was launched in 2004 on a long journey toward Comet 67P Churyumov-Gerasimenko. The spacecraft could not simply fly directly to the comet. It needed to gain speed and change direction by using the gravity of planets. Rosetta flew past Earth several times and also past Mars, allowing the planet's gravity to reshape its path like a series of enormous, invisible slingshots. The journey took about 10 years. During much of that time, Rosetta traveled through the cold darkness of the solar system. When it moved too far from the Sun for its solar panels to produce enough power, the spacecraft entered a long period of hibernation. Its systems were placed into a deep sleep. Then, in January 2014, Rosetta woke up. Engineers on Earth waited anxiously for a signal. After years of silence, the spacecraft finally sent a message confirming that it was alive and functioning. It had awakened hundreds of millions of kilometers away. Later that year, Rosetta reached Comet 67P. The first detailed images revealed a world unlike anything scientists had expected. The nucleus appeared to have two distinct lobes joined by a narrow neck, giving it a shape often compared to a rubber duck. But up close, it looked far more dramatic. There were cliffs, pits, smooth plains, deep shadows, fractures, dust-covered regions, and enormous boulders. Some cliffs rose hundreds of meters. The landscape looked both ancient and strangely fragile. Scientists believe the comet's two-lobed shape may have formed when two smaller objects collided very slowly and joined together during the early history of the solar system. This gentle collision may have happened more than 4 billion years ago. Rosetta did not orbit the comet in the same simple way that satellites orbit Earth. Comet 67P had very little gravity, and its irregular shape made navigation difficult. Gas and dust escaping from the surface also affected the spacecraft's motion. Rosetta had to perform a delicate dance around the nucleus. It followed a series of complex paths, sometimes moving closer and sometimes farther away. Its instruments mapped the surface, measured gases, studied dust particles, and observed how the comet changed as it approached the Sun. But Rosetta was carrying something else. Attached to the spacecraft was a small lander named Philae. Philae was designed to descend to the comet's surface and perform experiments directly on the nucleus. It was about the size of a household washing machine and weighed roughly 100 kilograms on Earth. On the comet, however, it weighed almost nothing. The gravity of 67P was so weak that a person could easily jump away from the surface and never return. A dropped object would fall very slowly. Landing in such conditions was not like landing on a planet. It was more like trying to settle gently onto a drifting mountain of ice and dust. On November 12, 2014, Philae separated from Rosetta. For about 7 hours, it descended silently toward the comet. There were no engines to guide it during the final fall. It relied on careful calculations and the weak pull of the nucleus. Engineers expected it to touch down at a chosen site and anchor itself with harpoons and screws. But the landing did not happen as planned. Philae reached the surface, but its anchoring harpoons failed to fire. Because gravity was so weak, the lander bounced. It rose back into space. The first bounce may have carried it hundreds of meters above the surface and lasted nearly 2 hours. Then it touched down again, bounced a second time, and finally came to rest in a shadowed location. No spacecraft had ever experienced a landing quite like this. Philae survived, but its final position created a serious problem. It had landed near a cliff or in a cavity where very little sunlight reached its solar panels. Its batteries could not last long. Even so, Philae began working immediately. It sent back images and scientific measurements. Its instruments studied the surface strength, composition, temperature, and structure of the comet. It detected organic molecules and helped scientists understand that the nucleus was porous, dusty, and much more complex than a simple block of ice. Philae worked for around 60 hours before its main battery ran out. Then it fell silent. For months, scientists hoped that as the comet approached the Sun, more sunlight might reach the lander. In 2015, Philae briefly contacted Rosetta again, sending a few signals before disappearing into silence once more. Its exact resting place remained unknown for a long time. Then, near the end of the mission, Rosetta photographed Philae tucked into a dark crack on the comet's surface. The tiny lander was visible with one leg raised awkwardly, confirming why its solar panels had received so little light. The image gave the mission a sense of closure. While Philae rested in the shadows, Rosetta continued to study the comet. As 67P moved closer to the Sun, its activity increased. Jets of gas and dust erupted from the surface. The coma grew. The spacecraft detected water vapor, carbon dioxide, carbon monoxide, oxygen, and many organic compounds. One of the mission's most important discoveries concerned the comet's water. Scientists compared the ratio of different forms of hydrogen in the comet's water with the water found on Earth. The match was not close enough to support the idea that comets like 67P were the main source of Earth's oceans. This does not mean comets contributed no water. Other types of comets may have different compositions, and asteroids probably also delivered water to the young Earth. The origin of our planet's oceans is likely a mixture of several processes. Rosetta also detected the amino acid glycine, one of the building blocks used by living organisms to make proteins. Finding glycine did not mean that life existed on the comet, but it showed that complex organic chemistry was present in the early solar system. Comets may therefore have delivered useful chemical ingredients to young planets. The mission also revealed how alive a comet can appear near the Sun. Cliffs collapsed. Cracks widened. Dust moved across the surface. Jets emerged from hidden areas. Parts of the landscape changed between observations. Even though a comet is ancient, it is not completely still. Sunlight reshapes it little by little. In September 2016, Rosetta's mission came to an end. The comet was moving farther from the Sun, and the spacecraft would soon receive too little power to continue operating. Rather than allowing Rosetta to drift away, mission controllers guided it slowly toward the nucleus. During its final descent, the spacecraft continued taking measurements and images. The surface grew larger and more detailed beneath it. Then Rosetta touched the comet and fell silent. Its journey ended beside Philae, on the same ancient world it had followed through space. There is something peaceful about that ending. Rosetta was built on Earth, traveled for more than a decade, crossed hundreds of millions of kilometers, and became a quiet part of the comet it had studied. Today, Rosetta and Philae are still there. They rest on the dark surface of Comet 67P as it continues around the Sun, moving outward into the cold and then, many years later, returning once more toward the light. Stardust and the particles brought home. Imagine holding a grain of dust that had traveled around the Sun for billions of years. It would be far smaller than a pebble, perhaps thinner than a human hair, yet inside it could be minerals formed before Earth had oceans, forests, or even a solid crust. Such a particle might preserve a tiny piece of the solar system's earliest memory. This was the promise of NASA's Stardust mission. Launched in 1999, Stardust was designed to do something no spacecraft had ever done before: fly through the clouds surrounding a comet, capture particles from it, and return those particles safely to Earth. Its main target was Comet Wild 2, pronounced Wild 2. Wild 2 is believed to have formed in the cold outer regions of the solar system. For most of its history, it probably traveled along a distant orbit, protected from the intense heat of the Sun. Then Jupiter changed its path. A relatively close encounter with a giant planet in 1974 pulled the comet into a much shorter orbit. Instead of remaining far away, Wild 2 began entering the inner solar system more frequently. This made it an excellent target for study. Because the comet had spent so much time in the cold outer darkness, scientists hoped its material would be less altered than that of comets that had repeatedly passed close to the Sun. Stardust carried several scientific instruments, but its most famous device looked surprisingly simple. It resembled a large tennis racket. The collector was filled with a delicate material called aerogel, an extremely light solid made mostly of empty space. Aerogel is sometimes described as frozen smoke because it appears pale, translucent, and almost weightless. But this fragile-looking substance had a remarkable purpose. Comet particles would strike the spacecraft at several kilometers per second. At such speeds, an ordinary metal collector might destroy them instantly. Aerogel allowed the particles to slow down gradually. As a grain entered the material, it created a narrow tunnel that widened near the surface and ended where the particle finally stopped. These trails looked like tiny carrots or miniature shooting stars trapped inside glassy clouds. The particles were still damaged by the collision, but many survived well enough to be studied. On January 2, 2004, Stardust approached Comet Wild 2. The spacecraft passed only a few hundred kilometers from the nucleus. As it moved through the coma, it encountered streams of dust racing away from the comet. The collector opened. For a few minutes, particles from Wild 2 struck the aerogel and became trapped inside it. Meanwhile, the spacecraft's camera photographed the nucleus. The images showed a surprisingly rugged world covered with depressions, cliffs, pits, and strange flat-bottomed features. Some formations may have been created by impacts, while others could have formed when gases escaped from beneath the surface. Wild 2 looked less like a smooth snowball and more like a battered, ancient landscape. During the flyby, Stardust had to protect itself. The dust around a comet may be thin, but particles traveling at high speed can be dangerous. The spacecraft was fitted with protective shields made from several layers of material. Even tiny grains could strike with enough energy to damage instruments. The shields were positioned in front of the spacecraft as it moved through the coma. Behind them, Stardust continued taking measurements and collecting material. After the encounter, the collector folded safely into a return capsule. Then the spacecraft began its long journey back toward Earth. In January 2006, the return capsule separated from Stardust and entered Earth's atmosphere. It arrived at extremely high speed, becoming one of the fastest human-made objects ever to return through the atmosphere. A heat shield protected the precious samples as the capsule glowed from intense friction and compression. Parachutes opened above the desert of Utah. The small capsule descended quietly and landed on the ground, carrying thousands of microscopic particles from a comet. After years in space, the material had finally arrived on Earth. Scientists transported the collector to a special clean laboratory. The challenge was enormous because most of the particles were incredibly small. Researchers examined the aerogel with microscopes, searching for the faint impact trails. In one unusual scientific project, volunteers from around the world were invited to help. Through an online program called Stardust at Home, participants studied images of the collector and searched for possible particle tracks. It was a rare moment when ordinary people could directly assist in the discovery of material from space. The first results from Wild 2 were surprising. Scientists expected the comet to contain mainly substances formed in extremely cold environments. Many of those materials were present, including organic compounds and primitive dust. But researchers also found minerals that form only at very high temperatures. One of these minerals was olivine, which is common in hot regions close to young stars. Another particle contained material similar to calcium-aluminum-rich inclusions, among the oldest known solids in the solar system. How could such hot minerals be found inside a comet that formed in the frozen outer regions? The answer suggested that the young solar system was far more active and mixed than scientists had once imagined. Material formed close to the newborn sun must have traveled enormous distances outward, reaching the cold region where comets were assembling. Powerful flows in the disk of gas and dust around the young sun may have carried hot minerals outward. Turbulence, magnetic forces, and gravitational interactions could all have helped mix the material. Comets were therefore not made only from substances created in one quiet, distant location. They were collections of particles from across the early solar system. A single comet could contain ice formed in deep cold, dust older than the planets, and minerals forged near the blazing young sun. That makes every comet a kind of cosmic mixture. Some stardust particles contained carbon-rich compounds, including complex organic material. These molecules were not evidence of life, but they showed that important carbon chemistry existed in the environment where planets formed. Later studies even found glycine, an amino acid used by living organisms on Earth. The glycine appeared to have an extraterrestrial isotopic signature, supporting the conclusion that it had come from space rather than being introduced after the sample landed. This discovery added to the idea that comets may have delivered organic ingredients to the early Earth. They may not have brought life itself, but they could have contributed some of the chemical building blocks from which life later developed. Stardust also collected particles from interstellar space. Before reaching Wild 2, the spacecraft exposed another side of its collector to the flow of tiny grains thought to be entering the solar system from beyond it. Finding these grains was far more difficult than locating comet particles. Only a small number of possible interstellar candidates were identified, and studying them required years of careful work. The mission demonstrated how much information can be hidden inside something almost invisible. A grain of dust can reveal the temperature at which it formed. Its isotopes can provide clues about its origin. Its minerals can record chemical reactions from billions of years ago. To the unaided eye, all such particles may look like ordinary specks. Under scientific instruments, they become archives. Stardust's journey did not end after the sample return. The main spacecraft remained in space and was given a new mission. It was redirected toward Comet Tempel 1, the same comet previously visited by NASA's Deep Impact spacecraft. In 2011, Stardust flew past Tempel 1 and photographed how the surface had changed. It also searched for the crater created several years earlier when Deep Impact deliberately sent a projectile into the comet. This extended mission allowed scientists to compare observations made during different passages around the Sun. Eventually, Stardust used nearly all its remaining fuel. Engineers performed one final test to learn how much propellant was left, information that could help improve future spacecraft designs. After that, the mission ended, but the returned particles remained. Unlike data transmitted from a distant spacecraft, physical samples can be studied again and again. As laboratory technology improves, scientists can return to the same tiny grains and ask new questions. A particle collected in 2004 may still reveal discoveries many decades later. This is one of the quiet strengths of sample return missions. The spacecraft's journey ends, but the science continues. Today, pieces of Comet Wild 2 are stored carefully on Earth. They are protected from contamination and distributed in tiny amounts to researchers. Each fragment is precious. Some are so small that they must be moved with tools finer than a needle. Others are studied with beams of electrons, X-rays, or lasers. Yet these grains once traveled freely through space. They escaped from the surface of a comet, crossed the path of a waiting spacecraft, slowed inside aerogel, survived a fiery return to Earth, and arrived inside a laboratory. For billions of years, they were part of the silent solar system. Now they are helping us understand how our world began. Frozen remnants from the birth of the solar system. Long before Earth had oceans, before the planets settled into their familiar paths, and before the Sun became the calm star we know today, the solar system was a vast, swirling cloud of gas and dust. Inside that cloud, comets began to form. Their story started more than 4.5 billion years ago, when gravity slowly pulled together material from an ancient nebula. At the center, pressure and temperature increased until the young sun ignited. Around it stretched a rotating disk filled with ice, dust, metal, rock, and simple organic compounds. The planets grew from this disk. Tiny grains collided and stuck together. Small clumps became larger bodies. Some eventually formed moons and planets. Others were scattered, broken apart, or pushed to the distant edges of the solar system. Many comets are survivors from this early era. They are not completely unchanged, but they preserve some of the most primitive material still available to scientists. While planets were heated, melted, compressed, and chemically transformed, many comet nuclei remained cold enough to protect ancient ices and dust. This is why comets are sometimes called time capsules. Their interiors may contain clues about the conditions that existed before Earth was fully formed. A comet nucleus is often described as a dirty snowball, but this image is only partly correct. Some scientists prefer the phrase icy dirtball because many comets contain large amounts of dust and dark material mixed with ice. Their surfaces can be almost black. This darkness comes partly from carbon-rich compounds that absorb sunlight. Even though comets become brilliant near the Sun, the solid nucleus beneath the glowing coma is often one of the darkest objects in the solar system. Inside, however, the material can be surprisingly delicate. Measurements from spacecraft suggest that many comet nuclei are highly porous. They may contain large empty spaces between grains of ice and dust, giving them a structure more like loosely packed snow than solid stone. Some comets are so light for their size that they could float in water, at least in theory, if an ocean large enough could hold them. Their low density tells scientists something important. Comets probably formed through gentle accumulation rather than violent compression. Tiny particles gathered slowly in the cold outer regions of the young solar system, creating fragile bodies that were never fully melted or tightly squeezed. The temperature of the solar system varied strongly with distance from the young sun. Close to the center, it was too warm for water and many gases to freeze. Only rock and metal could remain solid. Farther away, beyond a region known as the frost line, water ice became stable. Still farther out, extremely volatile substances such as carbon monoxide and nitrogen could freeze as well. This cold environment was ideal for comet formation. Many short-period comets are believed to come from the Kuiper belt, a broad region beyond Neptune filled with icy bodies. Pluto is one of its most famous residents, though it is far larger and more complex than a typical comet nucleus. The Kuiper belt is not a narrow ring. It is a vast population of objects moving on different orbits. Some follow relatively stable paths, while others are disturbed by Neptune's gravity and sent inward toward the Sun. When one of these bodies begins visiting the inner solar system, it may become an active comet. Many short-period comets belong to a group called Jupiter family comets. Their orbits are strongly influenced by Jupiter, whose enormous gravity can shorten, lengthen, or redirect their paths. Comet 67P, visited by Rosetta, belongs to this family. Long-period comets usually come from much farther away. They are thought to originate in the Oort cloud, a distant shell of icy objects surrounding the solar system. Unlike the flattened disk of planets and the Kuiper belt, the Oort cloud may extend in every direction. It could contain billions or even trillions of frozen bodies. The Oort cloud is so distant that sunlight there is extremely weak. Its objects may remain nearly motionless against the background stars for millions of years. Occasionally, however, something disturbs them. A passing star may gently pull on the cloud. The gravity of the Milky Way may shift an orbit. Interactions between distant objects may send one body inward. Then a comet begins a journey that can last hundreds of thousands or even millions of years. As it falls toward the Sun, gravity increases its speed. For most of its voyage, it remains dark and inactive. Only when it enters the warmer planetary region do its ices begin to turn into gas. Some long-period comets have never approached the Sun before. These are especially interesting because their surfaces may be less altered by repeated heating. Astronomers sometimes call them dynamically new comets. Their first close passage can be dramatic. Fresh ice may produce strong jets and a bright coma, but the nucleus can also be fragile. Rapid heating may cause it to fracture or disintegrate. Other comets have returned many times. Each passage removes material from the surface. The comet becomes smaller and less active. Dust may build into an insulating layer, covering deeper ice and reducing the amount of gas that escapes. Eventually, the object may become dormant. A dormant comet still follows a comet-like orbit, but it produces little or no visible coma. From a distance, it may resemble an asteroid. This shows that the boundary between comets and asteroids is not always clear. Asteroids are usually associated with rock and metal, while comets are associated with ice. But some asteroids release dust. Some comets become dry and inactive. Some objects appear to belong partly to both groups. The early solar system was not neatly divided. Material moved inward and outward. Giant planets changed position. Small bodies were scattered across enormous distances. Some models suggest that Jupiter, Saturn, Uranus, and Neptune migrated from the regions where they first formed. As they moved, their gravity disrupted countless icy objects. Many were thrown out of the solar system entirely. Others were sent into the Oort cloud. Some moved into the Kuiper belt. A small number were directed toward the inner planets. This gravitational rearrangement helped shape the solar system we see today. It may also explain why comets contain mixtures of materials formed at very different temperatures. High-temperature minerals discovered in comet samples suggest that matter from near the young sun traveled far outward before becoming part of comet nuclei. A comet is therefore not a simple piece of one distant region. It can be a collection of ingredients from across the early solar system. Inside one nucleus, scientists may find water ice formed in deep cold, minerals formed near intense heat, organic molecules created in space, and dust older than the planets themselves. All of it was gathered and preserved inside a small frozen world. Comets may also have played a role in shaping Earth. During the early history of the solar system, impacts were far more common than they are today. Comets and asteroids struck the young planets, delivering energy, water, carbon-rich molecules, and other materials. Scientists continue to debate how much of Earth's water came from comets. Some comet water has an isotopic composition different from that of Earth's oceans, while other measurements appear more similar. The answer may depend on the type of comet and where it formed. It is possible that Earth's water came from several sources. Some may have been present in the material that formed our planet. Some may have arrived inside water-rich asteroids. Some may have been delivered by comets. The same may be true for organic molecules. Comets carry carbon compounds, including substances related to amino acids and other ingredients used by living systems. These molecules are not alive, but they reveal that complex chemistry existed before planets became habitable. Perhaps comets helped enrich the young Earth with raw materials. In that sense, these distant, frozen bodies may be connected to every ocean, plant, animal, and person alive today. A comet seen in the night sky can therefore be viewed in two ways. It is a beautiful visitor moving through the present, but it is also a surviving fragment of the beginning. Its dust remembers the disk that once surrounded the sun. Its ice remembers temperatures from before Earth had a name. Its orbit carries evidence of ancient encounters with planets and stars. And as it glows softly near the sun, it opens a brief window into a time when the entire solar system was still being born. The hidden roads beyond Neptune. Far beyond the bright planets, where sunlight is weak and the sun looks more like a brilliant star than a warm presence, countless icy worlds move slowly through the dark. Many of them may one day become comets. These distant objects are not wandering randomly. They travel along enormous hidden roads shaped by gravity, ancient collisions, and the quiet influence of the giant planets. One of the most important regions is the Kuiper belt. The Kuiper belt begins beyond Neptune and extends through a wide zone of the outer solar system. It contains icy bodies of many sizes, from small fragments only a few kilometers across to dwarf planets hundreds or even thousands of kilometers wide. Pluto is part of this region. So are Eris, Makemake, Haumea, and many smaller worlds that remain too faint to see without powerful telescopes. The Kuiper belt is often imagined as a distant ring, but it is more complicated than a smooth band. Some objects follow nearly circular orbits. Others move along stretched paths. Many are tilted above or below the flat plane in which most planets orbit. Neptune plays a major role in organizing this population. Its gravity can trap objects into orbital patterns called resonances. In a resonance, two bodies complete their orbits in a simple numerical rhythm. Pluto, for example, completes 2 orbits around the Sun for every 3 completed by Neptune. This relationship protects Pluto from dangerous close encounters with the giant planet, even though their paths appear to cross when viewed from above. Other Kuiper belt objects are not so stable. Neptune's gravity can gradually disturb them, changing their orbits over millions of years. Some are pushed farther outward. Others are sent inward toward the region of the giant planets. When an icy body begins traveling closer to the Sun, it may eventually become a short-period comet. But the journey is rarely direct. A small object from beyond Neptune may first encounter Uranus. Then Saturn may alter its orbit. Finally, Jupiter may take control, shortening the path and turning it into a comet that returns every few years or decades. This movement can take a very long time. A future comet may spend millions of years passing between the giant planets before entering the inner solar system. Objects following these unstable paths are sometimes called centaurs. Centaurs are small icy bodies that orbit mainly between Jupiter and Neptune. They are named after the mythical creatures that were half human and half horse because centaurs in space seem to share qualities of both asteroids and comets. Some centaurs appear inactive. Others release gas and dust even though they are far from the Sun, where water ice should remain frozen. This distant activity may be powered by more volatile ices such as carbon monoxide or carbon dioxide. It may also happen when certain forms of ice change their internal structure and release trapped gases. One well-known centaur is Chiron. Chiron was originally classified as an asteroid after its discovery, but astronomers later observed a coma around it. This showed that it could behave like a comet. Another centaur, Chariklo, surprised scientists when it was found to have rings. These rings are much smaller than those of Saturn, but their existence around a tiny distant world revealed that the outer solar system can be far more complex than expected. Some centaurs may eventually be thrown out of the solar system. Others may collide with planets or the Sun. A few may settle into shorter orbits and become members of the Jupiter family comet population. Jupiter family comets usually take less than 20 years to circle the Sun. Their orbits are shaped strongly by Jupiter, the largest planet in the solar system. Its gravity is powerful enough to capture, redirect, or eject small bodies. Jupiter is sometimes described as a protector of Earth because it can pull dangerous objects away. But the reality is more subtle. The giant planet can indeed remove comets from certain paths, but it can also send them inward. Its gravity is neither protective nor destructive by intention. It simply reshapes whatever passes nearby. A close encounter with Jupiter can transform a comet's future in a matter of hours. A body that once followed a long orbit may suddenly be placed on a much shorter one. Another may gain enough speed to leave the solar system entirely. Comet Shoemaker, Levi 9 experienced an even more dramatic encounter. It passed so close to Jupiter that the planet's tidal forces tore it apart. The fragments formed a long chain and later plunged into Jupiter's atmosphere in 1994. This was the first time astronomers directly watched a major collision between two solar system bodies. The impacts produced enormous dark marks in Jupiter's clouds. The event reminded scientists that the outer solar system is not a quiet museum. It is active, changing, and sometimes violent. Yet most transformations happen slowly. An icy object may drift through the Kuiper belt for billions of years before a tiny gravitational change begins its journey inward. This is one reason comets are difficult to predict over very long periods. Every encounter matters. A distant pass by Neptune can slightly change the orbit. A later approach to Saturn can change it again. By the time the object reaches Jupiter, its path may be completely different. The process resembles a cosmic relay. Each giant planet passes the comet inward or outward through gravity. Not every comet comes from the Kuiper belt. Beyond it lies a more scattered population known as the scattered disk. Objects there often have highly elongated and tilted orbits, probably created by ancient interactions with Neptune. Eris belongs to this region. At its farthest point, a scattered disk object may travel many times farther from the Sun than Neptune. At its closest, it may return toward the planetary region. Some of these objects may be sources of certain comets. Even farther away may lie the inner Oort cloud, sometimes called the Hill's cloud. This hypothetical region could form a bridge between the scattered disk and the much more distant outer Oort cloud. The Oort cloud itself may extend almost halfway to the nearest star. No spacecraft has ever reached it, and no telescope has directly photographed an individual Oort cloud object. Scientists infer its existence from the orbits of long-period comets. These comets approach the Sun from every direction, not only from the flat plane of the planets. This suggests that their source is a vast spherical shell surrounding the solar system. The Oort cloud may contain a tremendous number of icy bodies. Some estimates suggest hundreds of billions or even trillions. If true, the total mass may equal several Earths. These objects probably formed much closer to the Sun, near the region of the giant planets. During the solar system's early history, gravitational encounters scattered them outward. Some escaped completely. Others were sent so far away that the gravity of passing stars and the Milky Way itself began to influence them. At those distances, the Sun's hold is extremely weak. A gentle tug from another star can shift an Oort cloud object enough to send it falling inward. The disturbing star does not need to pass very close. Even from a distance of light years, gravity can slowly reshape the cloud. Large molecular clouds moving through the galaxy may also disturb comet orbits. The tidal gravity of the Milky Way can gradually change their directions as well. These effects happen over enormous timescales. A comet leaving the Oort cloud may take millions of years to reach the inner solar system. For almost all that time, it remains invisible. It receives so little sunlight that even its frozen gases remain still. Its surface is dark, and it reflects almost no light toward Earth. Only when it reaches the region of the outer planets does it begin to brighten. At first, the change is subtle. Carbon monoxide or carbon dioxide may begin escaping. A faint coma forms. As the comet moves closer, water ice becomes active, and the familiar tail develops. By the time we discover it, most of its journey has already passed. A newly observed long-period comet may have begun falling toward the Sun before humans built the first cities. Its path connects time as well as distance. Some comets return after a few years. Others return after thousands. A few may never return at all. If a long-period comet receives a strong gravitational push from Jupiter, it can gain enough speed to escape the Sun forever. Then it becomes an interstellar traveler. It leaves the same outer roads that once guided it inward and begins crossing the galaxy. The solar system may therefore be constantly exchanging objects with the space between stars. Some visitors arrive from other systems. Some of our own comets leave for destinations unknown. The boundaries of the solar system are not solid walls. They are wide, quiet regions where gravity fades gradually and where frozen worlds move between belonging and escape. When we look at a comet glowing near Earth, we see only the brightest moment of a much longer story. Before the tail appeared, there were billions of years in darkness. There were distant orbits beyond Neptune, gentle gravitational nudges, and silent passages near giant planets. The comet did not suddenly appear. It followed a road so vast and so slow that only the universe could patiently build it. when a comet changes, breaks, or disappears. There is something gentle about the way a comet shines, but its journey near the Sun is not always peaceful. Beneath the glowing coma, the nucleus is being warmed, cracked, reshaped, and slowly worn away. Every return changes it. A comet may look graceful from Earth, yet up close it is a fragile world under enormous stress. Sunlight heats one side while the other remains cold. Gas pushes outward from beneath the surface. Dust slides down cliffs. Cracks widen. Jets erupt from hidden cavities. Sometimes, the nucleus can no longer hold together. Comets are often much weaker than solid asteroids. Many are made from loosely packed ice, dust, rock, and empty spaces. Their structure can resemble a frozen pile of rubble rather than a single hard body. This fragility is part of their ancient history. They formed gently in the early solar system, when small particles gathered in cold regions far from the young sun. Because they were never deeply compressed or melted, some retained a porous and delicate interior. For billions of years, that structure may remain stable. Then the comet approaches the Sun. Heat begins to move into the surface. Different materials expand at different rates. Ice trapped below a dusty crust turns into gas. Pressure builds inside cracks and cavities. If that pressure becomes strong enough, parts of the surface can burst outward. This is called an outburst. During an outburst, a comet may suddenly brighten within hours. A fresh cloud of dust expands around the nucleus, reflecting more sunlight and making the comet look much larger. To observers on Earth, the change can seem almost magical. A faint object may become visible through binoculars or even to the unaided eye. Then, over the following days, the new dust cloud spreads and the brightness fades. The cause may be a collapsing cliff, an opening vent, a pocket of trapped gas, or a newly exposed patch of ice. Some comets experience many small outbursts. Others undergo one enormous event. Comet 17P Holmes produced one of the most dramatic outbursts ever observed. In October 2007, it brightened by roughly 1 million times in less than 2 days. Before the outburst, it was a faint telescopic object. Afterward, it became visible without a telescope, appearing as a soft, round glow in the constellation Perseus. Its coma expanded until it became physically wider than the Sun, even though the comet's solid nucleus was only a few kilometers across. This is an extraordinary reminder that a comet's visible size can be very different from its actual body. The coma is vast but almost empty. Its particles are spread extremely thinly through space. Yet because the cloud is so large, it can reflect enough sunlight to become spectacular. Outbursts do not always destroy a comet. Sometimes the nucleus survives and continues along its orbit. But in other cases, the damage grows. A comet can split into 2 or more pieces. These fragments may remain close together for a while, each developing a small coma of its own. Over time, they drift apart. One of the most famous examples is Comet 3D Philae. It was discovered as a periodic comet and later observed to split into 2 separate nuclei. Eventually, both fragments disappeared from view. Although the comet itself was lost, its debris remained. The Andromedan meteor shower, which produced spectacular displays in the 19th century, was linked to material from Philae's comet. In this way, a comet can disappear but still return as light in Earth's atmosphere. Other comets fragment more dramatically. Comet Shoemaker Levi 9 broke apart after passing extremely close to Jupiter. The difference in Jupiter's gravitational pull across the comet was strong enough to tear the nucleus into many pieces. This effect is caused by tidal forces. The side of the comet closer to Jupiter was pulled more strongly than the far side. Because the nucleus was fragile, it stretched and separated. The fragments formed a long chain. In July 1994, they entered Jupiter's atmosphere one after another. Each impact released tremendous energy. Dark scars appeared in Jupiter's clouds, and some grew larger than Earth. The comet was destroyed, but the event allowed scientists to observe a planetary impact directly. Comets can also be torn apart by the Sun. A special group called sun-grazing comets passes extremely close to the solar surface. Some move through the Sun's outer atmosphere, the corona, where temperatures are extraordinarily high. Many do not survive. They may evaporate, fracture, or disappear completely. Some sun-grazers belong to the Creutz group, a family of comets believed to be fragments of a much larger comet that broke apart centuries ago. These fragments follow similar orbits and approach the Sun from nearly the same direction. Occasionally, one becomes bright enough to be visible in daylight. Most, however, are discovered by spacecraft that constantly observe the Sun. Solar observatories have found thousands of small sun-grazing comets. Many appear in images for only a short time before vanishing near the Sun. Their final journey may last millions of years, but their visible ending can happen in hours. Some comets survive a close solar passage but lose so much material that they emerge greatly weakened. Their tails may change shape suddenly. Their nuclei may split after perihelion, the point closest to the Sun. A comet can seem healthy on its way inward and then fade unexpectedly as it moves away. This makes predicting comet brightness extremely difficult. Astronomers can calculate an orbit very precisely, but they cannot always know what is happening inside the nucleus. A newly discovered comet may contain abundant fresh ice and become brilliant, or it may be covered in insulating dust and remain faint. It may brighten steadily, or it may break apart before reaching its expected peak. One well-known example is Comet Ison. Discovered in 2012, it was expected by some observers to become exceptionally bright during its close passage around the Sun in 2013. As it approached, excitement grew. But near the Sun, Ison appears to have disintegrated. For a short time, there was hope that part of it had survived. Images showed material emerging from behind the Sun. Yet the remaining cloud soon faded. The comet did not become the great spectacle many had imagined. Still, its disappearance was scientifically valuable. It revealed how difficult it is for fragile nuclei to survive extreme solar heating. It also showed that even an apparent failure can teach us something important. Comets are not performances created for human expectations. They follow the physics of their materials, shapes, histories, and orbits. Sometimes a comet does not break suddenly. Instead, it fades over many returns. Each passage removes ice and dust. The surface becomes coated in darker material. Active regions shrink. Eventually, almost no gas escapes. The comet becomes dormant. A dormant comet may look very similar to an asteroid. Without a visible coma or tail, it can be difficult to recognize its true origin. Its orbit may provide a clue. Objects with stretched, tilted paths are sometimes suspected of being extinct or dormant comets. An extinct comet has lost nearly all the easily vaporized ice near its surface. It may continue moving around the Sun for millions of years as a dark, inactive body. In this way, a comet does not always end with a dramatic breakup. It may simply become quiet. The bright tail disappears. The coma no longer forms. Only the ancient nucleus remains. This gradual fading may be the most common fate of periodic comets. Some will collide with planets. Some will fall into the Sun. Some will be thrown out of the solar system. Others will slowly wear away until they are no longer recognizable as comets. Yet even then, their material continues. Dust spreads along the orbit. Fragments become meteoroids. Atoms enter planetary atmospheres. Organic molecules mix with the wider solar system. Nothing truly vanishes. A comet may lose its familiar shape, but its matter remains part of the cosmic environment. The same dust that once formed a bright tail may later create a meteor. A fragment may rest on the surface of a moon. A molecule may drift through space for millions of years. This is one of the quiet truths of astronomy. Transformation is more common than disappearance. A comet is born from ancient dust and ice. It travels through darkness, glows near the sun, loses pieces of itself, and eventually changes into something else. Its beauty is temporary. Its material is not. And perhaps that is why a fading comet can still feel peaceful. It reminds us that endings in the universe are often only changes of form. How scientists discover and name new comets. Somewhere in the sky tonight, a faint comet may be moving toward the sun without anyone on Earth knowing it exists. It may still be too distant to form a bright tail. It may look like nothing more than a tiny blurred point among millions of stars. But sooner or later, a telescope may notice that this little point is moving. That is how many comet discoveries begin. Long ago, comets were usually found by people carefully searching the sky with the naked eye or through small telescopes. The observer would sweep slowly from one region to another, looking for a hazy object that did not match any known star cluster, galaxy, or nebula. This required patience. The sky is full of faint objects, and many of them can resemble a comet at first glance. A distant galaxy may appear as a soft patch. A star cluster may look blurred through poor atmospheric conditions. Even reflections inside a telescope can create misleading shapes. A true comet must move. An observer might record its position, return several hours later, and check whether the object has shifted against the background stars. If it has, there may be something new in the solar system. Today, most comets are discovered by automated surveys. Large telescopes repeatedly photograph wide sections of the night sky. Computers compare the images and search for points of light that have changed position. These surveys are often designed to find near-Earth asteroids, supernovae, and other changing objects, but they are also excellent comet hunters. One important survey is Pan-STARRS in Hawaii. Its telescopes scan the sky with powerful digital cameras, detecting faint moving bodies that would be almost impossible to find by eye. Another major project is the Catalina Sky Survey in Arizona, which searches for objects that could come near Earth. The Atlas Survey, whose name stands for Asteroid Terrestrial Impact Last Alert System, also watches large areas of the sky. Comets discovered by such projects often carry the survey's name. This is why modern comet names may include Pan-STARRS, Atlas, Linear, or NEOWISE. NEOWISE, for example, was discovered by a space telescope studying the sky in infrared light. Infrared observations are especially useful because they can detect heat and dusty activity that may not be obvious in visible light. Yet amateur astronomers still make important discoveries. Even in an age of automated telescopes, a careful human observer can notice something missed by large surveys. Some amateurs use backyard observatories with advanced cameras and software. Others live in regions of the world that are not covered as often by professional telescopes. The discovery of Comet 2I Borisov is a beautiful example. Gennady Borisov, an amateur astronomer in Crimea, discovered the object in 2019 using a telescope he had built himself. At first, it looked like a normal comet, but as astronomers measured its motion, they realized that its path was hyperbolic. It was moving too fast to be gravitationally bound to the Sun. It had come from interstellar space. A single careful observation had revealed a visitor from another star system. After a possible comet is found, astronomers must confirm it. The discovery is reported to the Minor Planet Center, an international organization that collects observations of small bodies in the solar system. Other astronomers are then asked to search for the object. They measure its exact position at different times, producing a sequence of observations called astrometry. From these measurements, Scientists begin calculating the orbit. At first, the result may be uncertain. A short observation period shows only a small piece of the object's path. It is like seeing a car for 1 second and trying to predict where it will be next week. As more observations arrive, the orbit becomes clearer. Astronomers determine whether the object follows a short-period orbit, a long-period orbit, a path through the asteroid belt, or perhaps an escape trajectory. They also examine whether it shows a coma or tail. If the object is surrounded by a fuzzy cloud, it may be classified as a comet. If it looks sharp and star-like, it may initially be classified as an asteroid. But this distinction can change. Some objects first discovered as asteroids later begin releasing gas or dust. When activity appears, they may receive a comet designation as well. This reflects the fact that the solar system does not always fit neatly into categories. The naming system for comets can look complicated, but each part carries information. A typical designation might look like C2020F3 NEOWISE. The first letter describes the comet's type. The letter C means it is a non-periodic comet, usually one with an orbital period longer than 200 years or one that has not yet been observed returning. The letter P is used for a periodic comet with a known orbit shorter than 200 years. Halley's comet is officially 1P a Halley because it was the first periodic comet to receive such a number. The letter D is used for a periodic comet that has disappeared, broken apart, or been lost. Comet Biela, for example, is known as 3D Biela. The letter X can be used when an orbit cannot be calculated reliably, often because the comet was observed long ago with limited records. The letter A may indicate an object first classified as a comet but later recognized as an asteroid-like body. The letter I is reserved for interstellar objects. Oumuamua is 1I Oumuamua, while Borisov is 2I Borisov. After the first letter comes the year of discovery. In C2020F3, the year is 2020. The next letter shows the half-month in which the object was discovered. Astronomers divide each month into 2 parts. The first half of January is A, the second half is B, the first half of February is C, and so on. The letter I is skipped to avoid confusion with the number 1. The letter F in C2020F3 means the comet was discovered during the second half of March. The number 3 means it was the third comet recorded in that half-month. Then comes the familiar name, often taken from the discoverer or the survey that found it. Traditionally, a comet may be named after up to 3 independent discoverers. This is why some comets have 2 names, such as Hale, Bopp or Shoemaker-Levy 9. Alan Hale and Thomas Bopp independently discovered Hale Bopp. Carolyn and Eugene Shoemaker, together with David Levy, were associated with the discovery of Shoemaker-Levy 9. The number 9 showed that it was the 9th periodic comet discovered by that team. Sometimes, a comet is named after a spacecraft or automated survey rather than a person. This is increasingly common because modern surveys discover so many objects. Still, behind every automated discovery are teams of engineers, astronomers, programmers, and observers. A comet's name may look technical, but it represents a human moment of recognition. Someone noticed that a faint point was not where it had been before. Once a comet has been confirmed and its orbit calculated, astronomers begin predicting its future. They estimate when it will pass closest to the Sun, a point called perihelion. They calculate how close it may come to Earth. They also try to predict its brightness. Brightness predictions are difficult. A comet can be large but inactive. Another can be small yet release huge amounts of dust. A newly discovered comet may appear promising while still far away, then fade as it approaches. Or it may suddenly brighten after an outburst. The behavior depends on the amount of ice, the structure of the nucleus, the angle of sunlight, and whether fresh active regions are exposed. This is why newspaper headlines sometimes promise a spectacular comet that later becomes disappointing. It is not necessarily because the original calculations were careless. Comets are simply unpredictable objects. Astronomers can calculate their paths far more accurately than their brightness. Another challenge is that some comets are discovered only after they pass the Sun. They may approach from the direction of the solar glare, where ground-based telescopes cannot see them. After perihelion, they move into darker sky and suddenly become visible. In other cases, solar-observing spacecraft discover comets extremely close to the Sun. The SOHO spacecraft, launched to study the Sun, has become one of the most successful comet discoverers in history. Its cameras block the Sun's bright disk, allowing scientists to observe the corona around it. Tiny sun-grazing comets often appear in these images. Many are fragments of the Creutz family. They brighten rapidly as they approach the Sun, then disappear. Some are found by professional astronomers, but many are discovered by volunteers who inspect SOHO images online. These citizen scientists search for tiny moving points that appear across several frames. A person sitting at home may become the first human to recognize a comet nearing its final hours. This is one of the most democratic parts of modern astronomy. A discovery does not always require a mountain observatory or a university position. It can begin with curiosity, patience, and careful attention. Future surveys will discover even more comets. The Vera C. Rubin Observatory is expected to photograph much of the visible sky repeatedly with extraordinary depth and speed. It will detect faint moving objects, distant comets, and perhaps more interstellar visitors. Astronomers expect that many comets currently hidden in the darkness will become known. Some may travel on unusual orbits. Some may be ancient objects making their first journey toward the Sun. Others may arrive from planetary systems far beyond our own. Each discovery adds another path to our map of the solar system. At first, a comet is only a point of light. Then observations reveal its motion. Its orbit tells us where it may have come from. Its brightness reveals activity. Its gases reveal chemistry. Its tail shows the influence of sunlight and the solar wind. A tiny blur becomes a world with a history, and there is something deeply calming in the way that knowledge begins. No sudden announcement from the sky. No loud arrival. Only a quiet dot moving against the stars, waiting for someone patient enough to notice. Did comets help prepare Earth for life? Imagine the young Earth more than 4 billion years ago. There were no forests, no birds, no quiet oceans reflecting the stars. The planet was hot, restless, and frequently struck by objects left over from the formation of the solar system. Among those objects were comets. They arrived from the cold outer regions carrying ice, dust, carbon-rich compounds, and material that had formed before Earth itself existed. This has led scientists to ask one of the most fascinating questions in astronomy. Did comets help make our planet suitable for life? The idea is appealing because comets contain large amounts of water ice. When a comet approaches the Sun, some of that ice turns into vapor and forms part of the glowing coma. Spacecraft and telescopes can analyze this gas and determine not only that water is present, but also what type of water it is. Water may seem simple, but not every water molecule is exactly the same. Most ordinary water contains 2 atoms of hydrogen and 1 atom of oxygen. But a small fraction contains a heavier form of hydrogen called deuterium. Scientists compare the ratio of deuterium to ordinary hydrogen in comet water with the same ratio in Earth's oceans. This ratio acts like a chemical fingerprint. If the fingerprints match closely, the comet may belong to a population that contributed water to Earth. If they are very different, that kind of comet was probably not the main source. Measurements have produced a complicated picture. Some comets have water with much more deuterium than Earth's oceans. Comet 67P, studied by Rosetta, is one example. Its water did not closely match the water found on Earth. Other comets have shown ratios more similar to our oceans. This suggests that comets are not all chemically identical. They formed in different regions, at different temperatures, and under different conditions. Some may have delivered water to Earth, while others probably did not contribute very much. Asteroids are also important. Many primitive asteroids contain minerals altered by water, and their hydrogen ratios often resemble Earth's water more closely than those of many comets. For this reason, a large portion of Earth's water may have arrived inside water-rich asteroids rather than comets. But the answer is probably not limited to one source. Some water may have been present in the material from which Earth formed. More may have arrived later through impacts. Comets may have added another smaller share. Our oceans could therefore be a mixture of water with several ancient origins. Every glass of water may contain atoms that traveled through very different parts of the early solar system. Some may have once been locked inside a small asteroid. Others may have been trapped in the mantle of the young Earth. A few may have arrived in the ice of a comet. Water, however, is only one part of the story. Comets also contain organic molecules. In chemistry, the word organic refers mainly to compounds built around carbon. It does not automatically mean that something is alive. Space is filled with organic chemistry. Carbon atoms can combine with hydrogen, oxygen, nitrogen, and other elements to form increasingly complex molecules. These compounds exist in cold interstellar clouds, around young stars, inside meteorites, and within comets. Missions such as Rosetta, Stardust, and Giotto have found evidence of many carbon-rich substances in comet material. Rosetta detected molecules including methanol, formaldehyde, ammonia, hydrogen cyanide, and glycine. Glycine is especially interesting because it is an amino acid. Amino acids are used by life on Earth to build proteins. Finding glycine on a comet does not prove that life exists there, but it shows that some of life's chemical ingredients can form naturally in space. Stardust also detected glycine in samples associated with Comet Wild 2. Its chemical signature supported an extraterrestrial origin. This means that amino acids or their precursors may have been present in the solar system before Earth became habitable. Comets may have acted as delivery vehicles. When they struck the young Earth, some of their organic material may have survived the impact or become involved in new chemical reactions. An impact is extremely energetic, and much of the incoming material can be destroyed by heat. But not everything is necessarily lost. Experiments and computer models suggest that some compounds can survive, especially in smaller fragments or during impacts at certain speeds and angles. Impacts may even create new molecules. The combination of pressure, heat, water, minerals, and carbon-rich material can produce complex chemistry. So comets may have been both carriers and chemical reactors. They delivered ancient substances and created temporary environments where those substances could change. Scientists do not believe that a comet simply arrived carrying a complete living organism that immediately began life on Earth. The origin of life was almost certainly much more complicated. It may have required liquid water, stable energy sources, useful minerals, repeated chemical cycles, and long periods during which simple molecules gradually became more organized. Comets could have contributed ingredients without providing the full recipe. This distinction is important. Flour alone is not a loaf of bread. In the same way, an amino acid is not a living cell. But without the right ingredients, more complex structures cannot form. Comets may have enriched the early Earth with carbon, nitrogen, water, phosphorus-related compounds, and other chemically useful material. Some researchers study a broader idea known as panspermia. Panspermia suggests that life, or at least very complex pre-life chemistry, might travel between worlds through rocks, asteroids, or comets. A large impact on a planet could throw fragments into space. Some fragments might contain microbes protected inside rock. In rare circumstances, they could reach another planet. Within one planetary system, this may be physically possible. Material has naturally traveled between Mars and Earth. Meteorites found on Earth have been identified as pieces of Mars, blasted into space by ancient impacts. Travel between different star systems would be far more difficult. The journey could take millions of years, exposing material to radiation, vacuum, and extreme cold. Yet interstellar objects show that solid bodies really can move from one star system to another. Whether life could survive such a journey remains uncertain. The idea is fascinating, but there is no confirmed evidence that life reached Earth this way. There is also a deeper question. If a microbe arrived from another world, panspermia would explain how life traveled, but not how life originally began. Somewhere, chemistry would still have needed to become biology for the first time. Comets may help scientists investigate that earlier stage. Their interiors preserve organic compounds formed under ancient conditions. By studying them, researchers can understand what kinds of molecules were available before planets matured. The more scientists examine comets, the less empty the early solar system appears. It was not made only of simple ice and stone. It contained complex carbon chemistry, molecules interacting with radiation, grains coated in organic material, and compounds capable of becoming part of living systems. Much of this chemistry may have begun even before the Sun formed. The solar system was created from a cloud of gas and dust that had been enriched by older generations of stars. Those stars produced carbon, oxygen, nitrogen, iron, and many other elements, then returned them to space. Inside the cold cloud that eventually formed the Sun, atoms joined into molecules. Ice grew on microscopic dust grains. Radiation triggered chemical reactions. When the solar system began forming, it inherited this ancient chemistry. Comets gathered and preserved some of it. They are therefore connected not only to the origin of planets, but also to stars that existed before our Sun. The carbon in a comet was once created inside an earlier star. The oxygen in its water also came from stellar processes. The material later became part of an interstellar cloud, then a solar nebula, then a comet. After billions of years, some of it may have reached Earth. The same chain of events created the atoms in our bodies. The carbon in human cells and the oxygen we breathe were formed by stars long before the birth of the solar system. Comets are a visible reminder of that shared origin. They carry the same cosmic elements that oceans, living cells, rocks, and atmospheres are built from. This does not mean that every comet carries life. Most are cold, airless, irradiated worlds without liquid water on their surfaces. But they carry possibility in chemical form. They show that the ingredients associated with life are not unique to Earth. Water exists throughout the solar system. Organic molecules exist in comets, meteorites, moons, and interstellar clouds. Amino acids can form without biology. The universe naturally creates complexity. Perhaps that is the most peaceful fact of all. Life may be rare, but the chemistry that supports it is widespread. Across space, atoms are constantly combining, separating, freezing, warming, and becoming part of new worlds. A comet drifting through darkness may seem lifeless and distant. Yet inside its ice are molecules related to oceans, atmospheres, and living cells. It may never touch a planet. It may simply pass the Sun and return to the outer darkness. But it still carries evidence that the universe has been preparing the ingredients of life for billions of years. The comets we have not met yet. Somewhere beyond Neptune, a small frozen world is moving quietly through darkness. It has no visible tail. No glowing coma surrounds it. No telescope on Earth has noticed it yet. For billions of years, it may have remained almost unchanged, preserving ice and dust from the earliest days of the solar system. Then, one day, gravity may slowly alter its path. Perhaps Neptune will pull on it. Perhaps a passing star will disturb its distant orbit. Perhaps the gentle tidal influence of the Milky Way will send it falling toward the Sun. Long before anyone sees it, its journey will already have begun. This is one of the most peaceful truths about comets. Many of the great comets of the future are already traveling toward us. They are still too faint and too distant to detect, but they are moving through the outer solar system along paths shaped by ancient gravity. Years, centuries, or even thousands of years from now, some will become visible. A faint blur will appear in a telescope image. Astronomers will measure its position, calculate its orbit, and realize that a new comet has arrived. At first, it may look unimpressive. Then, as it approaches the Sun, hidden ice will begin to turn into gas. Dust will rise from the surface. A coma will form. A tail will stretch outward into space. Something dark and almost invisible will become luminous. Future telescopes will discover comets earlier than ever before. Large sky surveys are becoming more sensitive and more frequent. Instead of photographing one region of the sky occasionally, modern observatories can repeatedly scan enormous areas and compare millions of points of light. Computers can detect tiny movements that human eyes might miss. This will allow astronomers to find comets while they are still far from the Sun. Early discovery is important. The sooner a comet is found, the more time scientists have to study it, predict its brightness, plan observations, and perhaps even design a spacecraft encounter. A newly discovered comet may remain active for months or years. By watching it from great distances, researchers can learn which frozen gases begin escaping first. Carbon monoxide and carbon dioxide can become active far from the Sun, where water ice remains frozen. Closer in, water vapor may begin to dominate. Each stage reveals a different layer of the comet. It is almost like watching an ancient object slowly open. Future missions may travel to comets before they become active. Studying a quiet nucleus in deep space would allow scientists to see its original surface before sunlight begins reshaping it. Other missions may follow comets through perihelion, watching cliffs collapse, jets appear, and dust move across the landscape. One especially ambitious idea is to wait in space for a comet that has not yet been discovered. A spacecraft could be launched and placed in a stable location, ready for years. When astronomers find a suitable new comet, the spacecraft could leave its waiting point and intercept it. This approach would be useful for long-period comets. Such objects may be discovered only a few years before passing through the inner solar system, which is often not enough time to design and launch an entirely new mission. A spacecraft already waiting would be prepared. It could visit a comet making its first known approach to the Sun. This would be scientifically precious. A comet that has never passed close to the Sun may preserve a more untouched surface than one that has returned many times. Its ice may contain gases that are normally lost during repeated heating. Its dust may reveal structures from the earliest stages of planet formation. A mission to such a comet would be like opening a container sealed for more than 4 billion years. Future spacecraft may also collect samples from comet nuclei. Stardust brought tiny dust particles back to Earth, but new missions could attempt to gather larger and more carefully protected material. A spacecraft might touch the surface, drill beneath the dark crust, collect ice, and seal it inside a refrigerated capsule. Keeping the sample cold would be essential. If comet ice warmed during the return journey, fragile gases could escape and chemical compounds could change. A cryogenic sample return mission would therefore be one of the most difficult projects in planetary science. But the reward would be extraordinary. Scientists could study untouched comet ice inside laboratories on Earth. They could measure its isotopes, minerals, salts, organic molecules, and microscopic structures with instruments too large and complex to send into space. The same samples could be preserved for future generations. Decades after their return, new technology might reveal information that today's instruments cannot detect. This has happened with samples from the Moon and asteroids. Material collected by one generation can continue teaching many others. Future Comet missions may also use smaller spacecraft. Instead of sending one large probe, scientists could release a group of miniature satellites around a comet. Each could study a different region. One might fly through a jet. Another might map the magnetic environment. Another could photograph the shadowed side of the nucleus. Together, they would provide a three-dimensional view of the comet's activity. Small probes might even land in several locations. One could settle on a dusty plain. Another could attach itself to a cliff. A third might enter a pit where fresh ice is exposed. Because every region of a comet can behave differently, multiple landers would reveal much more than a single landing site. Engineers may also learn to navigate around comets more safely. Rosetta showed how difficult this can be. The gravity is weak and irregular. Gas jets can push a spacecraft off course. Dust can damage instruments. The nucleus may rotate, changing the lighting and terrain beneath the spacecraft. Future probes could use artificial intelligence to react more quickly. They might identify hazards, adjust their paths, and choose safe landing areas without waiting for instructions from Earth. This would be especially useful when communication signals take many minutes or hours to cross space. Yet not every future discovery will involve a spacecraft. Telescopes on Earth and in orbit can study the light of comets in remarkable detail. A spectrum separates light into its component wavelengths. Certain molecules leave recognizable patterns in this light, almost like chemical fingerprints. By reading those patterns, astronomers can identify water, carbon monoxide, methane, ammonia, cyanide compounds, and many other substances. Future instruments will detect even fainter molecules. They may reveal more complex organic chemistry and show how comet composition differs between regions of the solar system. Astronomers may discover that comets formed in several distinct environments. Some may contain mostly material from the cold outer disk. Others may include larger amounts of dust transported outward from near the young sun. Some may preserve interstellar ice that existed before the solar system formed. Every comet could represent a slightly different chapter of the same ancient story. Interstellar comets will be among the most exciting future discoveries. Oumuamua and Borisov showed that objects from other star systems can pass through our own. There are almost certainly many more. Most are too small, too dark, or too fast to detect with current surveys. But future telescopes may find them regularly. An interstellar comet would allow scientists to compare our solar system with another planetary system directly. It would not be light traveling from a distant star. It would be actual material from that star's neighborhood. Its ice could have formed around another sun. Its minerals could have been shaped inside a completely different disk of gas and dust. Its chemistry could reveal whether other planetary systems are similar to ours. Perhaps many will contain water and familiar carbon compounds. Perhaps some will be surprisingly dry. Others may contain unusual mixtures that rarely occur here. Each visitor would expand our understanding of how planets and small worlds form throughout the galaxy. A future spacecraft might even intercept an interstellar object. This would be difficult because such visitors travel quickly and are often discovered only after entering the inner solar system. But with early detection and a spacecraft already waiting, a close flyby may become possible. For a few hours, humanity could study a body created around another star. Then it would continue outward, never to return. There is something beautiful about such a meeting. Two products of different star systems would briefly cross paths. The spacecraft would carry metals, electronics, and knowledge created on Earth. The comet would carry ice and dust from an unknown place in the galaxy. For a short time, they would travel together. Comets may also help us understand planetary defense. Most known comets remain far from Earth and present no danger. But long-period comets can arrive from distant regions and travel at very high speeds. Because they may be discovered later than asteroids, they can be more difficult to study in advance. Better surveys will improve our ability to detect them early. Astronomers can calculate whether an object will pass safely by Earth. Almost always, it will. If a future object were found on a dangerous path, early discovery would provide time to respond. Missions such as planetary defense demonstrations have shown that a spacecraft can alter the motion of a small body. Comets would present different challenges because they can be fragile, active, and surrounded by gas and dust. Still, understanding their structure would help scientists prepare. The purpose of this research is not to fear the sky. It is to know it better. The more objects we discover, the more accurately we can understand their paths. Knowledge turns uncertainty into preparation. Comets may also become destinations for human exploration one day. This possibility remains far in the future. A comet has almost no gravity, no breathable atmosphere, extreme temperature changes, and an unstable surface. Landing astronauts there would be extraordinarily difficult. Even walking would be strange. A gentle jump could carry a person far above the surface. Anchors and tethers would be necessary. Dust could cling to equipment. Jets might erupt unexpectedly. Yet comets could contain useful resources. Their water ice could be separated into hydrogen and oxygen, providing fuel and breathable oxygen. Other frozen gases and minerals might support exploration farther from Earth. Rather than transporting every resource from our planet, future travelers may learn to use materials already present in space. But perhaps the greatest value of comets will always be knowledge. They preserve a record that planets cannot. Earth's surface has been transformed by oceans, volcanoes, weather, plate tectonics, and life. Much of its earliest history has been erased. Comets experienced far less change. Their interiors may still contain material gathered before Earth was complete. To study a comet is therefore to study our own beginning. The dust inside it may be related to the dust that formed Earth. The ice may resemble substances that reached our young planet. The organic molecules may be connected to the chemistry that eventually supported life. Even though comets seem distant and alien, their story is part of ours. They remind us that Earth was not created alone. It formed inside a crowded disk filled with countless small bodies. Some became planets. Some became moons. Some collided. Some escaped. And some remained frozen, waiting in darkness. Future generations will see comets that we will never see. Children born centuries from now may watch Halley's comet return. Other observers may witness Hale Bopp after more than 2,000 years. Someone may discover a brilliant comet unlike any recorded before. They may stand beneath a dark sky and watch its tail stretch from horizon to horizon. They may feel the same wonder that ancient people felt. But their understanding will be deeper. They may know the comet's orbit, composition, birthplace, and age. Perhaps a spacecraft will already be traveling toward it. Perhaps a small lander will touch its surface while people watch from worlds beyond Earth. The future of comet exploration may look extraordinary, but the comets themselves will remain simple in their movement. They will continue following gravity. They will travel inward and outward. They will warm and cool. Their tails will appear and disappear. They will lose dust into space and carry ancient ice through the darkness. And long after our own lives have passed, they will continue their quiet journeys. A comet does not hurry. It may spend thousands of years completing a single orbit. It may remain unseen for almost all of that time. Then, for a few weeks, it becomes bright enough to capture the attention of an entire world. Perhaps this is the final calming lesson comets can offer us. Not everything meaningful needs to happen quickly. Some journeys are measured in centuries. Some transformations begin in silence. Some of the most beautiful moments are brief only because the path leading to them was so long. Tonight, even if no comet is visible above you, they are still out there. Some are moving beyond Neptune. Some are resting in the Oort cloud. Some are crossing interstellar space between distant stars. Others are already falling slowly toward the Sun. They carry ice older than Earth, dust from the birth of planets, and chemical memories from the ancient galaxy. And somewhere in the darkness, one of them may be beginning a journey that will someday light the sky for people who do not yet exist. Until then, it travels quietly. A small frozen world beneath countless stars, carrying the past into the future.